All right, in this section of the lecture, we're going to talk about TLC theory, and this starts our next assignment. So what goes on now that my samples have been made and extracted and placed in solvent and sprayed onto the plate with wonderful auto samplers from a company like K-Mag? Okay, what goes on? After this, I need to get the plate to do something. I'm going to have to separate the sample components from each other. Absolutely. So that's what this part of the lecture is going to be concerned with. So with that said, there's no other place to start than maybe my mobile phase. So the very first thing that I'm going to do is make a mobile phase according to the recipe that I am given in a laboratory situation. So again, terms and words, they're going to come back and haunt me. So I'm not really making mobile phase. I am actually, again, making developing solvent. That is what I'm making. I don't know about you, but that's what I'm making. I'm making developing solvent. But by making developing solvent, you're going to pour that into the tank. That is going to create a gas phase, and what you have left over in the liquid is the mobile phase. So if you're making the developing solvent, you are in a sense making mobile phase 2 at the same time. It's just going to be slightly different than the developing solvent that you have made. Now, if you're working with a pure solvent that is a neat liquid that has no other components or mixtures with it, then sure, mobile phase and developing solvent can be the same. But most often, they're going to have a mix. Even if it's a really tiny mix, they're going to have a mix. So we're going to make our mobile phase, and that's often the very first step. If you are under a method developing stage, so you're like research and developing and stuff, that's okay. You're just going to do trial and error. So the trial and error, you're going to run it, see how it looks, change up something a little bit, go run it again, see if it got better, see if it got worse, blah, 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 blah. And you're going to change these typically with very small percentages in the very beginning. So pick out something that you think is going to work. Pick a concentration percentage-wise, and then if that does not work as according to plan, then you change the percentage in little baby steps, and we've talked about that, and you see how it affects the separation. Do not do anything drastic. Do not do anything else other than small changes at one time. For the most of us, though, what's going to happen is that if we are employed and we are running this instrumentation in a laboratory setting, then these things have already been predetermined. I'm following a standard operating procedure. I am following a pharmacopoeia outline that we have to go through, that we have to obey if I'm working in the pharma or the food area. So these are different types of things that I will see. And for the most of us, we're not in research. We're not in developing. We leave those to other people, and then we just go in and actually do what needs to be done, and then we produce data, we generate it, print off those reports, give them to the quality units, and they'll be perfectly fine with that. This mobile phase then is going to open us up to the discussion yet again of non-polarity versus polarity. And we've talked about this a little bit now over and over and over and over. So we hope that we play off of the right types of situations when polarity is concerned. Polarity is not the only thing, like we've talked about before, that plays a role in the separation, but it is one of the major things that allow that to happen. So that's why we always refer to it. That's why we always talk about it. And we drop some of the other things that we've mentioned already at this point for that reason. So non-polarity versus polarity. So pick out the right stuff. It has been picked for a reason. Follow the recipe, follow the method, follow the SOP. Don't make any changes because just with a couple of percentages could be a make it or a break it moment for you, and you don't maybe want that to happen. So once I get the mobile phase made, once I get everything kind of squared away, again, developing solvent, I now need to pour it into a tank. And the tanks are going to come in different forms and in different sizes. It really depends on the intention of the TLC development. What are we doing with it? How accurate and precise do we need to be? Or are we just doing this to see some separation and be like a little neat experiment that even a middle school student can appreciate? That's what's going to go on in these chambers. So what you see here is an assortment of different things that we can use in TLC development. And the chamber here in the backhand side of that picture, that is a fairly standard size of chamber for our 10 by 20s or our 20 by 20 plates. So that is the kind of go-to measurement most of the time with TLC. And 20 by 10s are going to be used on the K-Mag instrumentation. But of course, if you're doing these by hand, you can go bigger and you can go smaller. It's not a big deal. So that's one option of a tank that I see back there. Here is another option of a tank, and I'm circling that now. And this is really for smaller, of course, a 10 centimeter, 20 centimeter plate cannot go in those little bitty things. But those are great for like microscope slides. So we got plates that look very similar to a microscope size, and they are covered in silica or alumina. They've got a glass backing. They make wonderful little test drives of plates before we ruin the real thing. And we've got chambers that are specifically meant for that type of situation. And if that's something that we want to do, then absolutely that option is out there for us. And it has little lids that we can screw on. We can get that gas phase to develop and whatever the case might be. So either way, these tanks are going to come in different shapes and different sizes, depending on what you need to run and what you need to analyze. We call them developing tanks. We call them chromatography tanks. These particular things are very often called Copland jars. And then at the same time, folks, we also have just straight up beakers. We can use a beaker. We can put some aluminum foil on the top of it, make sure that lip is not allowing vapors to escape. And it really does the same thing. I mean, we don't have to be fancy. We can use what we already have in our lab space to kind of get the point across and to test drive some of these things. That is not a big deal at all. But either way, we're going to have to grab a tank. And that tank is going to be filled with mobile phase, or AKA developing solvent. And we're going to have to let it sit in there for a little bit before we put our plate on the inside. Now, for the automation, for HPTLC, this is what your tanks will look like. This is where development is going to take place. So these are the ADC units, and A is for automated, D is for developing, and C is for chamber. Go figure! All right, so this is our developing chamber that we will begin using on our HPTLC instrumentation that we have in-house. So what happens here, up here at the very top, this is an area that's got a couple of components on the inside. There's actually a dryer that's built on the inside of this instrument, and it will pre-dry the plates for you. So as you spray and applicate your samples onto the plate, it's going to make sure it gets like a 5-minute drill with a hair dryer, some warm air, just to make sure that all of those solvents are in fact driven off of the plate. You don't want those on there. And that's just a quick little way that it can just send it a burst of air and get rid of that. Also, any type of loose silica that might still be present will also be blown away too at the same time. It's not a big deal. It should not be there, and it gives us a better separation. This door in the front, there's 2 buttons, one on the left and one on the right, that actually flips down, and that is where your plate is going to be inserted. So the plate is eventually going to make its way there, and you will close that trap door back up. Okay? Down here at the very bottom, this is where our tanks are going to be located. So there's our developing tank right there. And that is going to eventually have mobile phase or developing solvent added on the inside. So this is going to seal it off. There is a lid. It is sealed. It can't escape. That is part of the developing chamber. So I need a way to get my developing solvent on the inside. And that is the purpose of the 2 funnels up here at the very top. We're going to call it number 1 and number 2. We'll talk about why there's 2 that's going to be needed here in just a second, but we get 2 funnels that are up there at the top. I'm going to pour developing solvent into each one of them. So there's a certain amount that goes on the left, and there's a certain amount that goes on the right. for a reason. Again, we'll talk about a little bit later. So this is kind of the developing chamber that I would see with automation. The glass tank goes in the bottom. It's a little bit shorter because we're only doing 10 centimeter height plates, and it doesn't need to be as tall as some of the ones that we have in our lab that you've used manually already. But the tank goes down there. The developing solvent gets poured into the top, and then it drains into the tank down below in the appropriate areas. And then we wait for that tank to fill up with gas phase before we lower the plate on the inside. All right. So if I was doing this by hand, okay, so I'm going to go back, and if I was doing this thing by hand, there are some certain things that we want to remember as far as how the tank, the proper tank, is going to be made. If I look down the side of the developing tank, what I'll see here is a little hump in the middle. And that hump creates a trough area that's going to be in the front and another trough area that's going to be toward the back. If I look at it from the side, which is probably going to be a better view, that hump is going to be right here in the middle. So therefore, I get a little well in the front side of the tank and a small well on the back side of the tank. That is there for a reason, and we're getting ready to talk about that reason. So this is what we call a twin trough. Again, we've mentioned this before. So a twin trough chamber. TTC, if that's how you want to do it. There's other ways to abbreviate it. There's other ways to call it, but it is a twin trough chamber. All right, so when I place the plate in here, what needs to happen is that most of the time, for me, if I hand develop a tank, I choose the back well. And the reason that I choose the back well is because I'm going to lean the front part of the plate up against that area, and I rest the back of the plate against the glass of the chamber. That's the way that I lean it. So I can do that on the back side. I can do it on the front side. I just got to put the plate in a little backward, but I can do it on both sides, and I can develop two plates at the same time if I have the appropriate chamber to do that in. So I can put one in the back, and then I can put one in the front. It's not a big deal. Develop both of them at the same time, put the lid on them, and call it a day. Well, the problem here, though, is that that's not really the appropriate way to develop plates. The twin trough is in there for a different reason. And if you don't want to follow that reason because you don't have to and you're just playing around with some plates, then absolutely develop them this way. But really, for the most part, one trough is going to be dedicated to the plate, and another trough is going to be due to the saturation pad that we have to use in the plate development. That's why there's two chambers that are existing. All right, so when I place the plate in the tank, again, if I'm doing it by hand, I don't sit it straight up and down. I lean it, and that's the way that I will angle the plate inside of the tank for myself. All right, your automated tank developer chamber, that is going to operate in a slightly different way. Those plates are going to dangle. So as it lowers, it's going to lower it down into the tank, and it's going to hold it upright, and that's just the way that it's going to be held. So it is what it is. That's the way that it's going to perform its job. There's nothing wrong with that. It's not leaning, and it actually might give me some better data because of that. And it's not touching the surface of the glass tank at all, period, anywhere, on the bottom or on the sides. That's not the way that this thing is going to develop for me. So that's great news with our automated tank developer. That is one of the reasons that we want to use them. We want things consistent. We want things not damaged. We don't want things to come in contact with the plate surface and the silica. And it's one of the ways that it accomplishes the task. All right. When you place the plate in the chamber, a couple of things that you want to remember. Don't touch the sides. So you want to make sure that that sample does not rake up against the sides of the plate nor the sides of the developing chamber. And it should not be. You should not be spotting that far on the outskirts anyway in the first place. Next up, you should be using a pencil line, not a pen, and it should be above the mobile phase of the chamber. If it sat in the developing solvent, if it sat in that mobile phase that you were getting ready to use, what would happen is that your stuff would kind of be there and your spots would be down here at the bottom, and it would just seep out and it would go into the developing solvent. It would not go up the plate in a spot or in a band. It would actually go into the developing solvent, dissolve, go through the entire developing solvent, and then travel up the plate in an entire big, huge run. And you don't want that to happen. That is not allowing your components to separate on the plate because they've been dissolved off of the plate and they've went inside of the developing solvent and they've scattered across the entire surface, and it's not going to do anybody any good. So that is one of the things that you want to watch out for if you are hand developing the plates. So it is very important to only pour just enough into those developing chambers. And the reason is because if you pour too much and then you lower your plate on the inside and you're like, whoopsie, I made a mistake. Well, by that time it might be too late. And now your developing plate is ruined. All the work that you went in to spotting that plate is for nothing because now it's been submerged. It's not sucking that developing solvent up into the stationary phase and toward the tops of these plates. Immediately, as soon as they hit, that plate is going to start sucking up mobile phase for you. That's what you want. And the components are going to start traveling up the plate, of course, due to that movement. And that's exactly what we want to see. All right. We've talked about this before, but I think it's so important that I'm going to revisit it again. The stationary phase is typically silica, so SiO, 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 and then of course there's more things that happen on the lower side of the house, and they're not really with the silica. I need my eraser. Where's my eraser? Where's my eraser at? I don't know where my eraser is. Oh, well. So what we're going to see is that our silica is really what's going to kind of do the work for us. So let me kind of look at this. Oh, my gosh. I'll put it on the pen, and now it thinks that I'm erasing something that's not even supposed to be there. What is going on? Oh, no. Okay. So silica and silica and silica. I've got these other oxygens that are there, of course, and then on the silica I will see oxygens that are pointed on this end as well. And if that is the surface, these are the protonated oxygens that I have on the silica. So polarity is present, polarity is there in the stationary phase, polarity is there in the solvent. Absolutely, it's electronegativity driven, polarity driven, solubility driven. That's where the interactions are taking place unless they have been modified. So as these samples are going up the plate, they are interacting with the OH groups that are very polar, or we are replacing those OH groups by protonation of an alcohol, and we are replacing them with another group, whatever group that might be. So they are beginning to interact with that stationary phase. It could be straight up polar, it could be straight up non-polar with a modification, but they are interacting with it in some form, in some way. Again, it's all about the chamber, it's all about the development. This is kind of a simplistic way of using a beaker with some type of lid. A plate has been dumped on the inside of the beaker. There's some developing solvent here in the bottom. Notice my spot is above that developing solvent. So as capillary action takes over, as the plate is sucking that developing solvent up, there is only one way to go. And that one way is up, up, and away! And there we go, like our Elon Musk rocket ship. Into the atmosphere it goes. That is done by a pencil, not a pen. And then we start to see development and separation that takes place on the plate. All right. So that's just kind of part of the discussion that we need to have. In the next video, we're going to talk about other things that are needed inside of these developing chambers. So there's another important piece that we need to discuss, and we're going to talk about that. And that's what's going to happen next when you come back.